I'm really pleased to be here today to share my research on the evolution of red supergiants to supernovae, and hopefully I'll convince you by the end of the talk that these are a really cool object and really important for a whole host of events in the universe. So I'll start very simply by explaining to you all what a red supergiant is. So they are evolved massive stars between about 8 to 25, 8 to 30 solar masses, and they're really luminous. So in the Hertzsprung-Russell diagram, they're right up in the top right. There's famous examples such as Betelgeuse, which was in the news very recently. And these objects are the direct progenitors to type 2 supernovae, and knowing which ones are exploding and which ones aren't exploding is a very powerful test of stellar evolutionary theory. So the evolution of a massive star, let's say like a 15, 20 solar mass star, is expected to look something like this. It'll spend most of its life on the main sequence with a hydrogen burning core and an envelope. And at some point, the hydrogen in the core will deplete and you'll have a helium burning core surrounded by a hydrogen burning shell. And at this point, the envelope of the star will swell. And there's a lot of convection going on in the envelope. And these envelopes are thousands of solar radii. They are really, really extended objects. On a Hertzsprung-Russell diagram, it looks something like this. So the star will leave the main sequence and travel across at a pretty much constant luminosity until it lands in the red supergiant phase. So these are temperatures less than around 4,000 Kelvin. And we expect to see stars between, again, 10 to 30 solar masses reach this phase. For stars above that initial mass, they're not going to pass the red supergiant phase. There's this gap here called the Humphreys-Davidson limit, where we expect to see no red supergiants, and I'll explain to you why we don't see them there in a minute. But once they've landed in the red supergiant phase, you can be pretty confident that they're firmly on their path to supernovae. So here is a very, very basic overview of what happens during that time. So once they've arrived there, the lifetime is very short. They'll only stay as red supergiants for up to around 1 million years. Eventually, the helium in the core will get exhausted, fusing into carbon, which fuses into oxygen. So the core will fuse to heavier and heavier elements until eventually there are no more nuclear reactions in the core of and the star can't support itself against its own gravity. So that huge envelope comes crashing down, and you end up with a core collapse supernovae. But the type of supernova that you see depends very strongly on mass loss. So there's two classic options. So the first is that the star will hold on to its envelope because its mass loss rates are just not that strong, and it will die in the red supergiant phase as a hydrogen-rich supernovae. So it'll appear as a type 2 supernovae. That just means it's managed to hold on to its hydrogen envelope.
What's a YSG?
As a yellow supergiant. I should have taken that out. Don't worry about that. That's basically things in this kind of region where they've still got a hydrogen envelope, but we're not worrying about them today. For stars above that kind of 10 to 30 solar mass range, the mass loss rates are much stronger. So they never reach the red supergiant phase, and they will die as hydrogen poor supernovae, or type 1bc, or stars such as Wolf-Rayet stars, which are these really eruptive, massive stars we see. They're just like spewing off loads of material for a really long time, and they never reach the red supergiant phase. So that's a type 1 supernovae. But we do see red supergiants explode as supernovae. We're in a very fortunate time where, like now, when a supernova goes off, we can look back through our archival imaging and try and identify a progenitor. So you'll have a lovely picture of your supernova like this. And in HST imaging, you might be lucky enough to have multiple observations of that site in a few different wavebands. So this is a particularly nice example. So you go to the position of the supernovae, and you can see very clearly that there is a candidate object there. This one's particularly nice because you can see it's in color. We can see very clearly it is a red object that exploded. And then you can wait for the supernova to fade away and go back to that same location. And you can see now that the progenitor has gone. So you can be pretty confident that the star that was in your pre-explosion imaging was the one that exploded. And this is the most direct method of linking supernovae to their progenitors. It's actually quite difficult to get useful information out of these pre-explosion imaging though. What you want to do ideally is know which star is exploding, i.e. what is the initial mass of the star. For that, you need to work out a luminosity. But that example I showed you just there was a particularly nice one, multi-waveband. In reality, you'll probably only have one detection in maybe HST I band or something like that. So you have to make a lot of assumptions to convert that photometric point to a luminosity. So you start out with your photometry. You make an assumption about the color of the star, you make an assumption about the distance to the star, its extinction, and from that you can determine a terminal luminosity. And people like to take it a step further and use the terminal luminosity to determine an initial mass. And to do that, you need one of these initial mass terminal luminosity plots. So this just shows a few different examples from stellar models. So along the x-axis, we have the initial mass of the star, and along the y, it's the terminal luminosity. And you can see that for a given terminal luminosity, there's quite a spread on the initial mass that you can get for like one fixed terminal luminosity. So there's a lot of errors along the way, that a lot of uncertainties along the way, a lot of places that your errors could get bigger. But this is still the most direct way we have of linking the supernovae to their progenitors. But people have done this a lot, and very famously it was done in 2009 for basically all the type 2 supernovae within around 40 megaparsecs. So this figure just shows the initial mass, and then it's kind of like a cumulative plot of all the supernovae that have had their progenitors imaged in pre-explosion imaging. So if the distribution were to follow what we see for red supergiants in the field, or what we expect populations of red supergiants to look like, it should follow this line here. And instead, what we see is that the progenitor mass distribution follows instead this kind of shallower yellow line. And this got people wondering, what is happening to the high mass supernova progenitors? Why are we not seeing any stars in this kind of 16, 17 to 30 solar mass range explode? This was termed the red supergiant problem, and started people wondering, is the maximum type 2 progenitor mass 16 solar masses? Is it actually lower than the 30 solar masses that's been predicted and expected for a long time? But the question is then, what is happening to these high mass progenitors? So another solution that has been suggested is that maybe these objects in this higher mass range reach the red supergiant phase and then undergo extreme mass loss while they're in that phase, and that would cause them to shed their envelope and move back to the hot region of the HR diagram and die as a different type of supernovae, maybe not appearing as a type 2 supernovae at all. But the question is there evidence for these kind of mass loss rates during that phase? An important thing to note is how mass loss rates implemented in stellar models. So in stellar models, the mass loss rates are not calculated from first principles. We rely on prescriptions, and they're basically split into two different regions. So everything hotter than 10,000 Kelvin has a prescription for a hot star wind. In the hot star region, we kind of know what's going on with the winds. We know what's driving them. There are good analytical models that we can use to understand the winds in that region. For the cool supergiants, it's a bit of a different case. It's a bit of a different case. We actually don't have a good model of what's driving the wind there. We kind of think maybe we know what's driving the winds, but there's no good predictive model. So in the cool supergiant region, so everything cooler than 10,000 Kelvin, we rely on purely empirical prescription. So we're solely driven by observations of red supergiants. So my slides are in the wrong order and all that. Okay, so the question is, are these stars dying as different types of supernovae? So if we look at stellar models from, these are from 2000, you can see that they kind of follow the picture that I laid out at the start. So the 25 solar mass star reaches the red supergiant phase and it dies there. Above that mass, there is actually a quick red supergiant phase for that 40 solar mass star and it comes back out. And for 60 solar masses, it never gets anywhere near the red supergiant phase. But later set of models by this same group look a little bit different. So this time, if we follow the 15 solar mass track, you can see it dies as a red supergiant. But now the 20 solar mass star is leaving the red supergiant phase after experiencing some sort of mass loss that is enhanced. So the difference between these models, because they're from the same group, and the main difference between these models and the earlier models is how mass loss rates were implemented during the red supergiant phase. So in this set of models, following this kind of idea that maybe these mass loss rates are enhanced and that's what's driving stars away from the red supergiant phase, they ramped up the mass loss rate by an arbitrary factor of 3 to reproduce this kind of maximum type 2p progenitor mass. And that is the main thing that changed in these models. And the question is there observational evidence for these kind of mass loss rates during the red supergiant phase? So the prescriptions that these models rely on are purely empirical, and there is a lot to choose from. So this figure just shows a handful of the red supergiant mass loss rate prescriptions that are available in the literature. And you can see that for a given luminosity, you can end up with a very, very different mass loss rate at a given for a single luminosity. But most people pick this prescription. So this is the Diaga prescription from 1988. And I'm going to talk much more about it in a little bit. But within that one prescription on its own, there is huge internal scatter just from that single prescription of about plus minus a factor of 10. And just to put that into context for you, that is the difference between a star losing all of its envelope during the red supergiant phase or absolutely none of it. So it really is a huge level of scatter. Overplotted on this line are some observed mass loss rates for red supergiants. And again, you can see the different samples. There's a lot of scatter around that prescription. So this prescription was more of a literature study that came about in the 80s. So the author collected mass loss rates for basically as many stars as he could. So anything that had a mass loss rate and a luminosity in the literature was collected, including stars of all spectral types, including hot stars, and put together and was turned into a prescription. And that's a great idea, but it means that you end up with a highly heterogeneous sample. So there was no constraints on the masses or the metallicities that were going into the sample. Also, the way that the mass loss rates were worked out were all completely different. So some mass loss rates use mid-infrared excesses, other ones for the hot stars used kind of line analysis, but there was no homogeneity between the types of methodologies used to calculate the mass loss rates. And this is actually no longer used for hot stars ever, but it is still used for all cool supergiants in pretty much every single stellar model that's available. So for the red supergiants in this sample, there's only 15 available, and they were mostly things that were really easy to observe from the ground because a lot of the data came from the 60s, 70s, and 80s. So it was anything that was bright, so we're kind of skewed towards the most luminous red supergiants, and a lot of them were just like famous galactic sources. So if it had been imaged, it was probably because it was nearby, bright, and people liked it. And many of these objects have had their luminosities significantly revised since the days of this prescription coming about. So just to show you, so these red points show where the luminosities of these stars were in 1988. And for the ones that have had their luminosities updated, they've almost all come down by quite a bit. And their mass loss rates have also been revised downwards. And importantly as well, in this sample, over half of the stars have luminosities above a log L of 5.2. For comparison, in the LMC, there's only about 12% of red supergiants that are above this kind of luminosity range. So we're very skewed towards extreme objects, and the numbers that are in this prescription, which is widely used, are actually incorrect based on newer observations. But it is possible to do better. Oops, sorry. It's my summary of what's going on there. A group of stars that aren't representative and have incorrect luminosities. But it is possible to do better, and the one way you can do better is to look at red supergiants in clusters. And the reason to look at red supergiants in clusters is a few reasons. You can assume that all of the stars within there probably have the same metallicity. You can also assume that it's probably a pretty much coeval population for the red supergiants. Because the phase is so short as well, you can assume that every red supergiant you're currently seeing probably has the same initial mass to within about one solar mass. That's just because the lifetime is so short. So basically it's as if you're looking at a sample of red supergiants at the same initial mass. You're also more likely to have a well-constrained distance because it's easier to calculate distances to clusters and groups of stars rather than just single galactic objects that are just floating around. Every kind of bright red point in these images is a red supergiant. So you can see as well that just within this small sample of clusters, we have more red supergiants than were in the Diaga prescription. So we're also increasing the number of red supergiants with which we're analyzing to make a new prescription. So we used new data from Sophia, which is not that new anymore, RIP Sophia, as well as archival imaging from WISE, Spitzer, MSX. So anything mid-infrared was basically included in the survey to get new mass loss rates for all of these red supergiants. So how do we measure mass loss rates? It's quite simple for red supergiants because they have this sort of understandable structure. So you have your red supergiant, and then there's a big cavity, and at some point dust starts to form, and we can model this dust layer, which scatters the light out at longer wavelengths. So the light is absorbed at the shorter optical wavelengths and re-emitted, and we can model the mid-infrared excess and make some assumptions to get a mass loss rate prescription, a mass loss rate, sorry. This is what that looks like kind of on an SED. So the light is absorbed at the optical sort of wavelengths and then is re-emitted at around 10 microns. The shape of the bump that you see tells you about the dust composition. For red supergiants, it's usually this kind of silicate feature that we see, which just tells us that it's oxygen-rich dust. And this is just a little schematic, but in reality, the data looks something like this. So you basically just need photometry around this infrared feature, and then you can use radiative transfer codes. We use one called DUSTY to derive mass loss rates for each red supergiant. So you have to make some assumptions about, for example, the grain size, the grain density, the distribution of the dust around the star. But you can do all of that, and then you can pull out a mass loss rate for each of the stars in the sample.
Can I ask a question?
Yeah, of course.
This is getting you something about, it's like you're the dust mass.
Yes.
And then
we make an assumption about the wind velocity as well, based on observations of red supergiants.
Okay.
Yeah.
Great.
So we don't have individual wind velocities measured for each red supergiant, but the range is not that big. It's like 25 kilometers per second plus minus 10, and we include that in all the errors.
Size too, right?
You
need a mass at a time.
We fit for the position of the dust shell, so that comes out from the fitting.
That comes out from the
temperature. Yeah. So you measure like the dust temperature and get a best fit that way.
Okay.
Yeah. So we're fitting for the inner dust temperature basically.
Right.
Yeah.
Yeah. Thanks.
No problem.
Do you also need some assumption about the ratio of the dust to the gas?
Yeah, so we make an assumption about that as well, and that's kind of metallicity dependent. So there's different values for like the LMC or galactic, and we just have to go with our best assumptions on that because they don't have them individually measured. Yeah.
So we're discussing that. So what about the geometry? I mean, are you assuming completely spherical geometry or the opposite?
We assume a spherically symmetric wind at the moment, even though we know they are clumpy. So red supergiants do have like really clumpy winds, but when you're looking at them in a population like this, it kind of like averages out over time. So the stars that are more evolved, like closer to death, will like have more dust around them. So it kind of like, even though there's fluctuations, the overall trend can be well modeled.
Fragmented, it might
Yeah.
give you a different normalization.
Yeah, so we did test this using a 3D code as well, and we put the clumping factor up to like a ridiculous number, and it didn't make like a huge difference to the trend that I will show you in a bit. So we think that spherically symmetric modeling is fine for this type of thing. Yeah, cool. Yeah, so we model the emission using a radiative transfer code and derive a mass loss rate. And we also derive luminosities for each of the red supergiants by simply integrating under their observed SED. So rather than doing any model fitting for that, we just integrate under the data that we have. So this star actually does have optical data up here as well. It's just not included in this fit. And we just integrate under that to get a luminosity for all of the red supergiants. And once we've done that, we can plot the luminosities against the mass loss rates. And we could separate this by each cluster. So here, each different color symbol is a different cluster. So you can see these are the individual luminosity mass loss rate prescriptions for each cluster, and each relation has the same gradient within the errors. So what we did simply was fix the gradient, and from that we were able to derive and then what we found was that while the gradient is fixed, the offset of the relation does change with initial mass. So the stars that are over here are the younger, higher initial mass objects, and these stars are lower initial mass. So we were able to derive a new initial mass dependent mass loss rate prescription. And previously the mass loss rate prescriptions have only depended on the luminosity. They've never included mass loss rate. And when we compare our prescription to that Diaga prescription,
Sorry, I'm having trouble following.
Sure.
The initial mass is just coming from the age of the cluster.
Yes, exactly.
Okay.
Yeah. So the ones on the right are the younger clusters, and then they're more massive.
Thanks.
No problem.
And some stellar evolution.
Right, yeah. So to get like precise masses, you do have to use like a stellar evolution model. But what is like known for sure, well, the exact number of how massive they are is maybe slightly unknown. We know that those are younger and they're more massive. So that's kind of okay for this, but yeah. Okay. So when we compare this to the Diaga prescription, so these figures just show the residuals, so comparing the measured mass loss rate for each individual star versus what you would get from the prescription that you use against luminosity. These are the figures we see. So on the left is our new initial mass dependent prescription. So you can see that the scatter is a bit reduced, and there's obviously no offset because those were the stars that were used to make the prescription. On the right is the results when using the Diaga prescription. So you can see the scatter is increased, but also importantly, again, the stars on the right, the higher luminosity stars are the highest initial mass stars. You can see that the offset of those from the zero is really big. And what that means is that the start for the Diaga prescription is actually overestimating the mass loss rate in a much greater fashion for the stars that are the highest initial mass. And this is a problem because these are the stars whose fates are the most unknown.
Really quick, this
Yeah.
is the log residual.
Yeah. So, was that the same question?
No. There seems to be a bit of a trend with the residuals with the photometric luminosity apart from the offset points.
Yeah, going down.
Yeah, going down a bit.
I'm not entirely sure why that looks like that. I've thought it would be more flat. I don't know if it's just like the sample that they originally used or something, but yeah, I don't know. The trend is that the main trend to take away from that is that the highest initial mass objects have the worst offset, but I don't know why that slope is there.
It would make it even worse, right?
Yeah.
If the trend is a bit negative, then it would be even more offset.
Exactly.
Where it should be.
Yeah. Mm-hmm. Yeah, so those are the objects whose fate is the most unknown. So it's important for those that we do have a much better handle on what their mass loss rates are like so that we know how these stars are in their lives. So when we compare the amount of mass lost during the red supergiant phase from our prescription versus what is implemented in those stellar models that I showed earlier, this is what we see. So for a 20 solar mass star, the models that I showed before that show that turnaround from the red supergiant phase at 20 solar masses, they predict that a star during that million years will lose around 10 solar masses of material. And that's what's forcing the star back to the hot part of the HR diagram and making people predict that maybe these are dying as a different type of star. What we find with our prescription is that a 20 solar mass star would actually lose less than 1 solar mass of material during the red supergiant phase. So it actually would hold on to much more of its envelope than is suggested by those Geneva models. And then what this means is that these stars, there's no evidence for enhanced mass loss from the stars that we're looking at. Also, it means that these stars would not turn around and they would not leave the red supergiant phase after landing there. They would hold on to their envelope and they should still die as type 2 supernovae. Sorry. So the mass loss rates are actually far lower than what has been previously suggested. And that's before you even include these kind of like increasing the mass loss rates by an arbitrary factor. This is being backed up now by more recent work. So there was a paper last year which used a different method to calculate mass loss rates, also finding lower mass loss rates for red supergiants, and a paper that's come out just a few weeks ago, also finding that the mass loss rates are far lower than was previously suggested. So in this sample, there's no evidence for enhanced mass loss, but I do get asked a lot, what about short-lived phases that we're just not catching when we look at red supergiants and clusters? So these mass loss rates that we're measuring are not instantaneous. So the warm dust that we're measuring with the mid-infrared excess is probably sensitive to a few hundreds of years. But again, because we're looking at red supergiants and clusters, we're kind of like tracing the life of a star of a single mass. If there are enhanced mass loss rate phases that we're not catching in clusters because they're really quick, it would have to last 10 to the 5 years or more to remove 10 solar masses of material. So to remove that amount of material that you need to get the star to turn around, it would have to be a mass loss rate that is 10 times higher than what we're seeing and lasting a significant amount of time. So if there are enhanced mass loss rates, you would expect 10% of red supergiants to be undergoing mass loss rates higher than around 10 to the -4 solar masses per year. It's hard to probe that in clusters just because that is such a short time scale, you might not catch it. So what we needed to do was to look at red supergiants, for example, in the LMC. Some studies have suggested that there is this short-lived phase. So the Van Loon sample here, that's overplotted on the Diago 88 line, is supposedly a sample of red supergiants that show evidence of being extra dusty, so maybe undergoing these enhanced phases. They were termed dust enshrouded red supergiants, and they were thought to represent a phase that all red supergiants pass through. Oops, there they are. But if you look at the positions of the stars that are included in this Van Loon sample, so this dusty red supergiant sample, you can see that they don't stand out as like a distinct group in a color luminosity plot. So the color at the bottom just shows how red the objects are. So you might expect all of the stars in this dust enshrouded red supergiant sample to sit kind of in the top right of the plot. You'd expect them to maybe be brighter. You'd expect them to all be really dusty. But when you look at it on this kind of figure, you can see that they're kind of just scattered around. So it's not obvious how that sample was chosen.
Can you remind us how did they estimate their mass loss rate?
They did the same way that I did it. Yeah. So they had a sample that they said before they did that, these are dust enshrouded, and then they measured mass loss rates. So the orange section kind of shows where we expect normal mass loss rate objects to sit in this kind of color plot, and anything more red than that we would kind of term to be dust enshrouded. But you can see that a lot of these stars that were termed dust enshrouded sit on the less dusty side of this line. So it's not obvious how that sample was chosen, but those stars form the basis of a prescription that is also implemented in some stellar models. But what would a dust enshrouded red supergiant look like? They should be really, really easy to spot, because they should be so dusty that they are significantly fainter in the optical and have these really huge bumps that are like the 10 micron bumps. It should be significantly different to the ones that we kind of see for normal red supergiants. Like the figure I showed before, there's a little bump, you can measure a mass loss rate, but it doesn't look anything like that. But they should be easy to spot in theory. So we looked in the LMC and we fit these kind of models to every red supergiant that we could see, and we derived their luminosities. And this was what we found. So the black points are just every red supergiant, and the ones that are highlighted in red are the ones that were included in that Van Loon dusty red supergiant sample. So again, you can see that that red sample doesn't stand out as a distinct group. But also what we see is that to fit into that criteria of having mass loss rates strong enough to force the evolution to change, the stars would have to land in this pink box up here. So they'd have to have mass loss rates higher than this. And we actually only see one object that is up there, and it's a star called WHG64, which is a super weird red supergiant. It looks odd. It's really dusty. It's highly asymmetric. Some people think it might actually be the product of like binary evolution or a merger or something like that. But we don't see anywhere near enough red supergiants in this kind of region to explain, to suggest that there is an enhanced mass loss rate phase that all of these stars are passing through.
So just so I understand,
yeah,
the Van Loon line here is lower than the Van Loon points.
Yeah.
And the y-axis here, all the dots and triangles, those are your numbers.
Yeah.
Yeah, but your numbers roughly agree with their numbers?
Roughly, yeah.
I see.
There are very slight differences in like the assumptions we make in our modeling, but it's not enough to cause this kind, like if I plotted the Van Loon numbers on here, it wouldn't like suddenly jump up.
So like that original plot where you showed the Jaeger and then you showed Van Loon, that circle is sitting above the Jaeger, you're just saying that's probably right, but it's not enough.
Yeah.
Okay.
Yeah. Yeah, so the line is like kind of dragged up as well. So these objects that are triangles are like quite dusty, but they're actually more likely to be AGB stars based on like their temperature and how they look. So they're included in the sample as well. And AGBs are lower mass stars with different mass loss mechanisms, and they have different, they get dustier than red supergiants do generally. So I think what's happened is that those stars have like kind of pulled the trend up.
Oh yeah, that's very significant.
Yeah. That's my hunch on it. But yeah, the numbers roughly agree. So like we don't have like huge discrepancy. The main issue is that I don't know how they pick their sample, but it's often touted as like all red supergiants have this dust enshrouded phase because of this sample, but they're not an obvious separate sample from the rest of the population. So again, when you look at WOH-G64 compared to the rest of the population, this figure just shows the extinction from the circumstellar material for the stars in the population. You can see that the extinction from WOH-G64 is massive compared to the other stars. So it just sits out as a weirdo. It's probably not a single star. It's not evidence for a phase that all red supergiants pass through. But even if it was, having one red supergiant look like that out of the entire LMC population, it would mean that the time frame was not long enough to cause a significant difference in the evolution of these stars.
What's the sample size?
It's like 200 and something. Yeah. Okay, so if there is a dust enshrouded red supergiant phase, it must be very short-lived, and it wouldn't be long enough to force stars back to the hot side of the HR diagram. And what this means is that there's probably no single star route to produce these kind of hydrogen poor supernovae. So none of the stars that we're seeing would be losing enough mass to turn around from the red supergiant phase. We expect they would stay there and hold on to their envelope. And above 30 solar masses, most stars are kind of in binaries. So it could be that there's no single star route to produce these stripped stars at all.
How short exactly did you calculate sort of?
I did, and I can't remember the number. It's really short, okay. Like 1,000 years or so, okay. Less than that, maybe, that order. So the normal mass loss rates during a red supergiant phase, the quiescent mass loss isn't enough to force them to turn around. There's not good evidence for stars having enhanced mass loss rate phases and turning around. So could there be anything else that is stopping stars from in the higher mass range producing type 2 supernovae? There is another suggestion that is often made, and that is that maybe these stars are actually forming black holes with no explosion. So the sort of typical path we expect for red supergiants is that everything between 10 to 30 solar masses will explode as a supernovae and leave behind probably a neutron star remnant. Another suggestion that's been made in light of these kind of missing red supergiants is that maybe the upper mass limit to this is not 30 as we've suspected, but it's actually lower. And rather than explode, these objects are just collapsing to form a black hole with little or no visible outburst or explosion. And this has been suggested by theory and maybe too by observations. And this is something that I've been working on very recently. So this figure, again, just shows the kind of cumulative distribution of all the type 2 supernovae that have had their progenitors imaged with the pre-explosion photometry. Along the bottom, we have the results of a set of models where they ran a bunch of models and they worked out at the end of each model, would this star explode or not explode based on something called the compact factor, how compact the core is. And so the green lines mean that the star would end its life as an explosion, and the black points mean that the star would end its life as an implosion. And you can see that once you get above like 16, 17 solar masses, the islands of implosion, as they're called, get bigger. So it's more likely in these models that a star above that kind of mass would implode and not produce a supernovae. So that's the line there. So maybe they're less likely to explode, and this is why we're not seeing high mass supernova progenitors. And we may have seen one direct collapse event, and it actually lands quite neatly in one of these islands of implosion. It's called N6946BH1. So this is the first failed supernova candidate. And what we know about it is that prior to its disappearance, it appeared as a red supergiant with a luminosity of around 5.5. So this would be around a 25 solar mass red supergiant. It had a very moderate outburst and then it disappeared. So this is an HST image of it in 2007. And when you go back in 2015, the star appears to be completely gone in the optical. And so this was suggested that maybe it had formed a black hole, but there was no way of really testing this without, suggested that it had formed a black hole. But to rule out other options, you need JWST. So another option is that the star could just be hiding behind dust. So I showed you those enhanced mass loss rates before, and I showed you that the stars that are more dusty would have much higher extinction at the optical. And so it was suggested as well that maybe the star is hiding. Betelgeuse kind of did this a few years ago. It had like a dimming event. And there's also a star in a nearby galaxy called M51, which appeared to disappear, but then came back a few years later when we went back and re-observed it.
Regarding this one, this is what object is this in?
It's in the fireworks galaxy, NGC 6946.
Okay, that's
yeah. So there's a lot of supernova there.
And we observed it between 2017. Like this didn't go supernova.
No.
We missed.
No.
Okay.
So it was found because there's a group that are like scanning a bunch of galaxies regularly. So and there's observations of its outburst, which I'll show in a little bit, but it definitely it definitely did not go supernova. Yeah. But the only way to kind of like distinguish between these objects is to look with JWST and see, is there anything still remaining that we just can't see in the optical? And I was very fortunate to get JWST imaging of the source, and what we found was that a source does remain at the site of the star that has supposedly disappeared. So I got NIRCam imaging, so the top row of 4 wavebands of NIRCam, and the bottom is MIRI imaging. So the bottom ones are more probing the dust. The top ones, some of them are comparable to some HST imaging. For the first time, we saw that the source actually is a little asterism of 3 stars. So 2 of them that are there don't contribute much to the flux at all, so we can kind of ignore them. And based on the centroid, we're pretty confident the bottom one is the source that was there in the HST imaging. But you can see in the MIRI imaging in particular, there's still quite a bright source. So the luminosity of the source, when you integrate under all of this, comes out to be a luminosity around 4.7, which is around 13 to 25% of the progenitor luminosity. So it is significantly fainter. It is significantly fainter than the source that was there before, but there is still a source. So how do we interpret that? What does it mean? So the first question is it a failed supernovae? Does it make sense? But the issue with the failed supernova model is that the models themselves are still not really able to make testable predictions. So people are working on it, but the predictions are hard to test with these observations. So some people suggest that the outburst from a kind of event like this, you do expect to see a little transient, should last around 500 days. The outburst from this object was shorter, around 200 days. Some people suggest that there should be lingering infrared flux, so that might be fine that we're seeing it in JWST. But the prediction is that it could last anywhere from a few minutes to a few thousands of years, which is not very constraining. There's also the issue that there's been no X-rays detected from this source. And you can imagine if a star had collapsed to form a black hole immediately and left kind of an envelope around it, you might expect to see some X-ray emission because that should be quite an energetic event, but there has been 0 X-rays detected. So maybe not a failed supernovae. What else could it be? Oh, sorry, and this is another figure as well. So these are some models that show what you might expect the kind of outburst from a failed supernovae to look like. It's a little bit of a complicated plot, but basically, the energy is shown on the y-axis, and the little star shows how bright this paper suggests a 16.5 solar mass red supergiant should be if it collapsed and forms a little outburst. And you can see it's brighter than N6946BH1. So the outburst, maybe for a failed supernovae of 25 solar masses, should be brighter than what we saw for N6946BH1. But those are very new models. So other people disagree with this, but the point is that there are a lot of models that make kind of conflicting statements about what a failed supernovae should even look like, which makes it difficult to test. Another option is that perhaps there was some sort of stellar merger. So there are a lot of non-terminal low luminosity transients that we see in the universe all the time. And they often involve binaries and mergers or mass transfer events. So there's intermediate luminosity optical transients, luminous red novae, there's luminous blue variable eruptions, supernova imposters. And could this scenario explain the luminosity? Maybe. So this image shows Eta Carina, which is an LBV, which very famously has had outbursts and looks super weird now. You can really resolve its dust. It's highly asymmetric. There's been times where it's looked, so LBVs are quite hot, but there's been times where it's looked like a red supergiant. There's been times where it's looked fainter, it's changed in brightness. But you can see that it's a highly asymmetric event. So a merger for a star is highly asymmetric and would result in this kind of weird dust shell. And depending on the orientation of the dust shell, you could actually block out a lot of the light completely. So you may actually only see 10 to 20% of the emitted flux, depending on the viewing angle. So maybe a stellar merger could make sense. Another kind of evidence for this is if you look at the light curve of the failed supernovae before it had its outburst. So this, so the blue, red, green lines are the kind of optical bands, and then the black and gray are kind of mid-infrared, kind of tracing the warm dust sort of lines. So the point here is the 2009 was the outburst. So you can see it had a little outburst, nowhere near as energetic as a supernovae. But prior to the outburst, you can actually see that the source was getting redder. So you can see that the fluxes and the Spitzer bands are kind of brightening. I'll draw it on if you can't see it. And this kind of behavior is a little weird. Actually, earlier than 2008, the source didn't look like a red supergiant at all. It actually looked like a yellow supergiant, so it looked hotter, it was less red. So it's evolved towards a cooler temperature prior to its little outburst. And it actually looks very similar to a known merger event, V1309. So this was lower mass, but it was a merger of two stars. And prior to the merger event, you could see the stars brightening and reddening. And this is termed, well, it was termed for this object, the star's death spiral. As the stars spiral in towards each other, they pull off loads of material, pull off loads of dust, which makes the source appear redder. And then it had its little outburst before settling and appearing much fainter. So what we see for, what we see for BH1 is kind of consistent with this picture of having two stars spiraling in on each other. Sorry. So we may not even have been seeing the progenitor to BH1 in its quiescent state. So while people are saying it's a 25 solar mass red supergiant that collapsed, it might not actually have been a 25 solar mass red supergiant. It could have been a lower luminosity object. It might be that we're not recovering all of that flux because we weren't seeing it in its quiescent state. But at the minute, what we need ideally is more data. So we need to keep following BH1, ideally every few years with JWST. And if we do in-depth radiative transfer modeling, we should be able to put meaningful limits on any potential surviving star. So here are some nice 3-color images of the source. So hopefully we'll be able to follow the star again in future JWST rounds and see, is it fading, and see if that can rule in or out whether it's actually a failed supernovae or whether it was some sort of merger. And so I'm at the end of my talk, so I'll just leave up my conclusions and I'm happy to take any questions.
Very nice talk, thank you. Moving back to sort of the first question I asked about the mass loss estimates and the dust to gas mass ratio. The dust to gas mass ratio that you're using, I would imagine it wouldn't necessarily be the normal one that you use everywhere else in the galaxy, because this is sort of where you're forming dust, right? So are you using the normal value, or how uncertain is it? Because I would imagine if this is the place where you're forming dust, you may have a lot more dust than you would elsewhere.
Sure. So we do use like the kind of standard galactic numbers, but observations of like red supergiants with like interferometry kind of support the numbers we're using to within like some error bar. And you can measure it individually for each star, but it takes a lot of telescope time to do it. So unfortunately, that is something we have to make an assumption on, but there's no reason to think that the ratio would be off so much that it would increase the mass loss rates by like a significant factor.
How do you directly measure the dust to gas mass ratio?
Yeah, it's very fiddly, and I don't have a quick answer for you on that, but it's a fiddly process that takes a lot of time and it's not super fun.
So can you go back to your slide where you kind of make the point that it's very unlikely that red supergiants undergo this like very high split phase. Yeah, so yeah, this one. So basically here you have a sample from LMC, red supergiants, and you only see very few, maybe just one star up in the upper right
Yep.
corner. The thing is, and so you're making a case that, it's 1% of the sample.
Yeah.
So this can only be a very short time scale.
If that star's even representative of the rest of the red
But
supergiant.
what is the distribution of masses in this sample? I mean,
it should cover like the whole range technically.
Right. So I guess that here my point would be that most of the stars that you're looking at are lower mass red supergiants.
Probably.
And so, it's unlikely.
So the fraction's bigger.
And you only expect this like higher muscle strength to occur in the more massive one, the one about 20 solar masses that you expect to maybe, remove their envelope. And so you have to weight this from some IMF and star formation history.
Yeah.
So, if that's 1 in 100 star, I could imagine that this is like maybe 1 every 10 stars more than 20 solar masses, which means that we'll just need this to be doing it for like 10 to 4 years, which at that muscle state can remove the end.
I see what you're saying. And I think, well, part of the issue with this star in particular is that it doesn't look like a normal red supergiant like at all. So I think we have a bit of a problem in massive stars where people will see one weird thing and be like, oh, everything must do that because it's like obviously a short lifetime. But what I'm hoping to do is to like expand this to like different galaxies and then really look for these like short-lived enhanced mass loss rate phases if they are there. If that is a phase, like that one star, like it's super weird and I don't know why it would do that. Like it's really asymmetric. It's got this like odd torus. It's a super isolated star, which also kind of suggests to me that it was probably the product of like a binary thing and it's been rejuvenated. So I wouldn't use that one object to like draw a conclusion about the entire population, but unfortunately, like this is the only galaxy that we can do this for at the minute, and hopefully we'll be able to look to other galaxies and really like test it.
When you derived mass dependent and luminosity dependent mass loss rates, it looked like the mass loss rate was actually kind of mass independent, right? Like in this picture, all the mass loss rates are like 10 to the minus 6 per year, even though the luminosity is like a decade and a half larger. Yep. Is there a way to understand the physics of that process? Does that give you some hint of what's doing the driving of the mass loss?
Yeah, that's work in progress. I am hoping to use that because the kind of picture in my head is that all stars, the stars that are the higher initial mass are just brighter when they get to the red supergiant phase, but they all arrive there with no dust. So I am hoping that maybe this could like tell us about, what is driving the mass loss rates, or like trying to like put some numbers to it that is kind of, we can extrapolate. Unfortunately, in this picture, all of these clusters are kind of the same initial mass, which was unfortunate and not what I wanted when I got their masses. But there does seem to be like a clear offset. Like the young ones are significantly more massive, like 10 solar masses, 12 solar masses bigger. So I'm hoping to work on that, but I haven't got around to it yet.
Yeah, I think what Bill said, I mean, I think it's a very interesting
and
surprising result.
Yeah.
Pretty much it's saying that you can take 2 stars at the same point in the HR diagram. They look identical.
Yeah.
But one is more massive. For some reason, that one is driving higher mass loss rate. It's very different from
so the one that is more massive would have a lower mass loss rate, right?
Yeah, so
that same point,
which is even more.
Yeah. So it was weird.
Can I ask a question about, you're following a lot of these other observations up now with JWST, which is not a surveying instrument. How rapidly can you follow up, populations of red supergiants? Which are you going to just run out of time?
So I'm not following up any of the clusters that we have data for already, but there are surveys with JWST already that have got populations of red supergiants in. So there's the JWST FANG survey, which is looking at like 50 galaxies or something like that. And they've imaged them in like super high resolution. So I'm hoping to go through the clusters that are available, because that's all publicly available data as well. So I'm hoping to use that to like probe this kind of relation at different metallicities and distances and ages and all that. For an object like N6946BH1, I do have to like apply every year for that, and it's not always successful, but like hopefully people will see it's a useful object, then we can, it's worth following up because it's a bit weird. But yeah, for these clusters, you wouldn't get much by looking at them with JWST. For one, they're too nearby and too bright anyway, but also you're just not going to learn anything new with the mid-infrared photometry.
Yeah, I may have answered it in my own head, but I was thinking about Roman, what you may or may not be able to do.
Yeah.
I'm not familiar with how its bands sort of lay on the sort of infrared spectrum that you need to do these mass loss rates. Is it helpful in that regime, or is it not red enough?
It's not quite red enough for the mass loss rates, but where it will be really useful is that there are like surveys proposed, just image like nearby young galaxies. So for the work where people are estimating progenitor luminosities using the pre-explosion photometry, I'm hoping that more supernovae will go off that have like more complete SEDs, and then we should be able to get better initial masses for those, because as I showed like quite early, when you only have one photometric point, like the errors are like really big. And also something I'm working on at the minute is that what you see is that if stars do have mid-infrared photometry available in the pre-explosion imaging, you always estimate a higher initial mass than you do for when you've just got a single thing. So this whole like missing red
super. You just have a single what?
Wait, when you have a single photometric point.
Okay.
Yeah. So a lot of them imaging in I band, and obviously for red supergiants, that's not ideal because they're more red. What you want is the mid-infrared photometry to get a better handle on if there's dust there, what kind of color it is, like how evolved is it, because there's a lot of corrections that go into like turning like a photometric point into a luminosity, and there's even more errors when you only have optical. So Nancy Grace Roman will be really useful for that type of work, and yeah, that's what I'm hoping for to get from it.